Welcome to lecture 25. So, today we will talk about the lambda notation. Most of today's lecture is going to be like a history class. So, it's not going to be too deep except historically. Right. So, the point is long ago in the year 1900, the great German mathematician David Hilbert actually in the World Congress of Mathematicians, he enunciated a program for the next century, which is just closing now in a few years. So, he said that the outstanding problems that are going to govern mathematics in the 20th century are going to be the notions of what exactly is the notion of a computation, right. So, the main question Hilbert wanted answered was how much of mathematics is actually mechanically computable, I mean is actually computable by a machine, and what he wanted was not the actual presence of machines, but he wanted a logical concept of what constitutes mechanical computation. So, which means that you are really looking at some very fundamental nature of a computation. If you look at the scenery at that time, firstly the fact that some things are mechanically computable was already known, because for example Pascal and Leibniz had created mechanical calculators. I mean Pascal his father was some kind of an accountant or some such thing, and he had to do lots and lots of arithmetic. So, Pascal decided that this whole thing was getting out of hand. The best thing to do was to use gears and so on and so forth, and create a calculating machine. And in fact, Pascal was quite successful. I mean what he created as a calculating machine with gears and wheels and using gear reduction and so on and so forth is very close to the registrix machines that used to be available till a few years recently. I mean he had the carry and borrow and so on for arithmetic integer operations, and Leibniz had similarly, since Leibniz was originally itself interested in the concept of what is probably now called linguistic philosophy, he was interested in the notion of symbols and symbol pushing and so on and so forth, and the closeness with which differentiation is associated with division led Leibniz to come out with this notation for for derivatives which we use commonly now. So, there was a large amount of stuff that predated the current linguistic philosophy from Leibniz and Descartes onwards. Also there were lots of other things which were, for example the people were aware of. One is the Jacquard loom. For example, the Jacquard loom consists of what might be considered a primitive stored program concept, in the sense that there is a card with holes in it, and you use that card essentially to weave patterns on a cloth. So, if you in fact the first Jacquard loom probably came up in the 18th century, and very complicated patterns. For example, if you were to see the Balucheri saris, which were produced in Bengal in the turn of this century and the last century, they actually are the first instances of the use of an automatic loom with a stored program concept to define weavings in such a fashion as to come out with thematic designs on cloths. I mean they are not just repetitive designs. I mean there were whole themes like the Kurukshetra war, or the Bhagavad Gita or some such thing. One whole sari would just have a picture of have a weaving which denotes these things. So, those cards were probably the first programs if you were to look at it fairly objectively for a certain model of computation which is not which is other than mathematics, right. Okay. And also well known were these music boxes. For example, this is a music box which contains some, it is a programmed music box. The whole idea is that if the music is sufficiently good, then the thief who comes to steal your jewelry will just stand perplexed there and will be caught by the police. Right. So, the whole thing was these mechanical music boxes were very common, for example, in Switzerland, and they use a clock mechanism, and a whole song could be programmed with just wheels and gears and so on and so forth. I am rather scared of my wife, so I can't pull it apart and show you the actual music box, but rest assured that it is a purely mechanical contrivance which just whirring gears and wheels and a certain amount of ratchet pinion mechanisms and so on. So, music boxes, and there are some gigantic music boxes which were produced in those days because a countess will probably have such a large amount of jewelry, you require a really mammoth music box for her. So, and the first machine, actual machine with mechanical machine was created by Babbage on paper, and the first programs were written by Countess Ada Lovelace, a niece of Byron, for example. So, Lady Ada Lovelace actually wrote programs for Babbage's analytical engine in a notation which could be read through cards very much like in a Jacquard loom and could be translated into. The fact is that Babbage's machine was never produced, it is still there as blueprints if you like. He never had the money and nobody would finance him, but Ada probably gave the first proper notation for writing programs for computations on Babbage's machine. So, with all this as a background, it was natural that the concept, and there were other things. I mean, the notion of an algorithm was sort of informally known for the last 2000 years, starting from Euclid's algorithm for GCD, the C of Eratosthenes, the work of Al-Khwarizmi and so on and so forth. And so, the question therefore boiled, and if you look at the 1900s and so on, Russell and Whitehead's book on the Principia Mathematica had just been published at Russell's own expense because nobody would buy it, nobody would touch it. So, and it was the heyday of linguistic philosophy, and the whole point, the whole philosophical movement at that time and logical movement at that time was to somehow define everything rigorously through the syntax of a language, right. So, an important problem that Hilbert raised in his program when he spoke about mechanical computation was really that, well, we know Euclid's algorithm is an algorithm, we know various things are algorithms. So, the question is what exactly is an algorithm? Why is not a calculation of convergence to a limit an algorithm, for example? Is that, or is that an algorithm at all? Why are certain, why can we, how can we think of certain things as algorithms and what are not algorithms? And once, so fundamental to Hilbert's program was the question of having to actually define the notion of an algorithm. It had to be accurately defined, and only after you have known only after you have defined the notion of an algorithm or given a sufficiently precise characterization of what exactly constitutes an algorithm, only then can you really talk about mechanical computation, a model of computation which is based on algorithms. Only then you can talk about what part of mathematics is actually mechanically computable. I mean, for example, can theorems be proved mechanically? Can we talk about Hilbert spaces? Is Cantor's diagonalization a mechanical procedure? What about the proofs of geometry? What about the constructive proofs of geometry? What about the proofs by contradiction? Are they all mechanically computable? Could a machine have come out with these proofs? I mean, these are the sort of questions that were raised by Hilbert's program, and there were several attempts in different ways. One was to take the actual view that really what Hilbert is talking about is construction of a machine. I mean, is there a machine which you can construct? The second is Hilbert's questions are merely of a logical nature, and so do they have to be answered logically, purely mathematically, right? So these different aspects were actually taken up by different people. So one is, of course, so the questions finally boil down to loosely speaking, what is mechanically computable, and next what is an algorithm. And a large amount of consensus, because of the prevailing linguistic philosophy atmosphere there, the Vienna school and Russell's Principia Mathematica and so on, it seemed more or less clear to most logicians and mathematicians that really what should go into the basics of an algorithm or a computation is symbol manipulation. And somehow we have to think of computations in terms of symbol manipulation. And then the whole idea was that any other thing which looks mechanical could probably be converted into a notation of symbols, and then we could think of it again as symbol manipulation. So, and this symbol pushing was quite an attractive idea, because a large amount of algebraic computation was really symbolic manipulation, and with logic being described in a purely symbol pushing way, a large amount of mathematics, it looked like, could actually be expressed completely in terms of symbol manipulations, right. So in fact, theorem proving, I mean, the whole idea of defining a logical language, a set of inference rules which were very closely related to symbol pushing, was actually to algebraize geometry. A previous algebraization of geometry was by Descartes, in the sense that he actually transformed all geometrical principles into pure algebraic principles in coordinate geometry. But Descartes' notion never actually exploited symbol manipulation to a very rigorous extent. And the whole idea was, what constitutes geometric reasoning? What makes Euclid's elements rigorous? What constitutes a rigorous proof? Why isn't the parallel postulate provable from the other axioms of Euclid? And so the question is, the only way one could think of actually looking at what constitutes correct geometric reasoning is if somehow you could make theorem proving in geometry also somewhat mechanical. Then everybody could be assured that if you enunciated the principles of a proof in purely mechanical terms, then most people may not be able to prove any theorems, but at least most people would be able to check whether a proof is correct, right. So if the symbol pushing followed a certain set of rules, a finite set of rules, then you could be at least assured that a proof of a theorem is right. Now if it is going to be symbol pushing, then what is theorem proving also mechanically possible? What kinds of theorems are mechanically provable? If you look at the algebraic theorems, a large amount of them are really mechanical symbol processing and could perhaps be done by a machine. Now, if you can convert geometric reasoning also into some logical language, into some logical notation, use pure symbol mechanisms, no notion of meaning, just purely through syntax, if you could define inference rules, then perhaps even a large amount of theorem proving in mathematics could be done mechanically. Even if you do not attribute creativity to a machine, at least the checking of a proof could be done by a machine, right. So, that is the reason when you learn logic, you learn logic in with as a purely symbol processing discipline, right. So, the question was and then there was also in the rest of pure mathematics, there was also the question of foundations of mathematics. I mean, there were lots of things which are not understandable. So, in cleaning up the foundations of mathematics, they decided that what is fundamental to mathematics is the notion of sets, and that all of mathematics was being rewritten so that it conformed to sets as a basic notion in mathematics. By sets, we are talking about the membership, the empty set, and equality of sets, and so on and so forth. So, all of mathematics was actually rewritten, including Euclidean geometry, because there were lots of linguistic problems with the construction of proofs in many of Euclid's in many of the theorems enunciated by Euclid. While they were more or less rigorous, there were lots of ambiguities, there were lots of sometimes there were hidden assumptions which made one theorem actually dependent on a theorem that came later. So, the notion of circularity had to be removed, and a large amount of and so most of mathematics was being rewritten in terms of sets, in terms of a collection of postulates or axioms. But in all this, the question again of what exactly constitutes a computation, and is it really different from that of the rest of mathematics? Can you use sets themselves as a basis of computation, describing computations? It is not clear actually, and there was a school of thought started with Schoenfinkel and which never gained much appreciation only in the last 20 years, called combinatory logic. So, he used symbol processing as a basic mechanism to define a set of rules for what he called a computation, right. But and that led to the development of combinatory logic, mostly through the efforts of Haskell-Curry. Schoenfinkel himself did not gain any reputation for what he did, but Curry took it up, and for the next 60 years he actually developed it into a fairly perfect programming language, he and a lot of his followers. So, there is this programming language called Haskell, which is based on Curry's combinatory logic, which is the interpreter for which was written less than 7 years ago. But probably a more important influence was that if you are looking at computations, then what you should consider basic to computations is the notion of a function. So, this was a view enunciated by Church, Alonzo Church. He was at Princeton University at that time. So, his basic idea was that sets might be basic to mathematics, but what actually is basic to computation is the notion of a function. And his whole idea was to answer Hilbert's main question: what exactly is mechanically computable, by using functions as the main notion. But there is a problem. If you look at set theory when in mathematics, then since everything else is to be defined in terms of sets, you cannot posit the existence of individuals. Okay, so the only foundation that is there in mathematics is that of a set itself. I mean, what is there is just the empty set. Everything else, numbers, ordinals, cardinals, functions, everything should be defined in terms of the underlying set theory. And the idea was set theory itself should be defined in terms of defined as an exercise in first order logic definition, right. So, the axioms and the postulates of set theory should be clearly enunciated so that you get a clear consistent view of sets. You also allow you somehow allow infinite sets through the infinity axiom and so on and so forth. You also allow you have to, through the axioms you have to capture the fact that sets cannot contain a membership relation that is infinitely descending, but at the same time there is no basic element except sets itself, and there should be no assumption of individuals. So, individuals, since sets are supposed to be a conception of the mind and do not bear any relation to reality, and since all of mathematics is to be expressed in terms of sets, the only way you could define sets is through a collection of axioms, very much like the only way you could define points, lines and planes in Euclidean geometry is through a collection of axioms which characterize the properties of points, lines and planes. You cannot use a definition, because if you use a definition, then you are assuming the existence of something else which is more basic for the concept. So, the only way to define sets is to use characterizing axioms for which will exactly characterize sets, which will not allow the construction of other kinds of sets which somehow lead to inconsistencies. There are lots of them, like Russell's paradox and Burali-Forti paradox and so on and so forth, which I will not go into. So, now if you take a similar view to computation, and if you regard functions as the most basic element of computation, then all that you can think of is take a first order logic like view. That means, you have an infinite collection of variable symbols, and you have to define the notion of functions somehow by just manipulating these functions, these symbols, right. And so, there is no question of these variable symbols are all indistinguishable in terms of, there is no notion of types. For example, types have to be built up later somehow. They are all just equally, each symbol is as good as any other, and they do not have any special status except for some, since any first order logical language has some basic constant symbols. So, the only distinction you can have are constant symbols and variable symbols, right. So, and actually the analogy with sets Church found was quite proper. For example, you have two ways of defining sets. One is you can define them by enumeration, or you can define them by abstraction. Defining by enumeration is your the roster form, as they call it in school, and defining by abstraction is the set builder form, as they call it in school. And when you define by abstraction, you are usually using a logical predicate to define a set. So, the first order logic, and it has to be a first order logic predicate, so similarly, if you look at functions, there are two ways. You can actually define them by enumeration, or you can define them by abstraction, right. And actually what you can do, what Church showed is also that sets are also really functions. If you look at them carefully, for any infinites, for any subset of some given universe, you may define a set as really the membership predicate. So, any set which is contained in a universe U is really a function from this universe to, is really a predicate, if you like, okay. So, and therefore has a logical status of a predicate, and really I can think of this set, okay, as a function to which I can apply a value. Okay. So basically if E is the set which denotes the set of even numbers defined by abstraction, then E applied to 5 is false, E applied to 8 is true, right. And what do you do when you actually do a function application? I mean, you actually take, so if let us look at this set definition more carefully in view of whatever we have done in programming languages. So there is a binding occurrence of x here and there is an applied occurrence of x here. There is a binding occurrence of y here which is actually bound by this quantifier and an applied occurrence of this y. So if you look at this predicate, x is free in this predicate and y is bound. Okay. So what does function application mean? Function application means that you take this, you take a set binding occurrence of this x and not a binding created by quantifiers. You take a set binding occurrence of this x and apply the value 5 to it, apply this take 5 as an argument, and your resulting predicate is obtained by a syntactic substitution of 5 for x. Right. So what you are essentially doing is you are taking all free occurrences of x here and syntactically replacing them by 5, and that is function application. So, and this function application is actually very much ML like. So, it is like an ML like functional application, and we might think of it as a pure syntactic substitution. I mean, this we can think of this expression or this predicate as being obtained from this predicate by an application of this function on 5. And what does function application mean? Function application just means a syntactic replacement in the body of this function of all free occurrences of this bound variable by the argument. And in fact, what Church felt was that our normal mathematical notion of functions and their function application was exactly that, except that mathematicians over the last 2000 years were a little careless about notation. And so the whole idea was to somehow clean up that notation and make two things very clear. One was that mathematicians usually confused function definition from function application in their notation. It was never very clear except when they explicitly told you verbally what is a function definition and what is actually a function application, because the only way mathematicians knew to define functions was by their application onto some argument. Okay. So, if you were to take a function, let us say you take a polynomial like this, okay. So, it was verbally stated that a, b and c are constants, maybe a is not 0 if they really wanted it to be quadratic, and the whole idea was that there is this notion of there is a function, this thing is a function, but I cannot express it in any way except by actually defining the effect of that function on an argument, on an arbitrary argument x. So, all function definitions were function definitions by applications, right. So, so the point was that very often mathematicians would use something like this, to denote that there is this concept of a function which I do not know how to define, but let us say I have defined its effect on an argument x like this, then I am now defining a value which is the value obtained when this function is applied to this value x naught. Okay. So, there was no distinction except by verbally specifying what is arbitrary and what is particular. They could not really, they never really distinguished between function definitions and function applications, but actually conceptually they are two different things, and so that conceptual difference has to come out in their notation. The conceptual difference between the definition of a function and the value obtained by applying that function onto an argument are two different things, and they should and the difference in the two concepts should come out.
So I didn't understand it. I mean, sir, how can we define a function otherwise?
Right. So how can we define a function otherwise? Exactly. How did you define the set as a function? You bound the variable, right? So you just bind this variable.
But sir, we ultimately have to apply it to some arbitrary.
Yeah, sure. So you have to give application rules, right? All that Church wanted to say was that there is a conceptual distinction between definition of a function and the effect of the function on an argument, and that conceptual difference was more or less obscured in all mathematical texts. That conceptual difference was only made clear verbally by specifying that let this x be some arbitrary thing, or actually specifying consider the function f of x equals this. Now at the value x naught, consider f of x naught, but this f of x naught is not a function, f of x naught is a value. I mean, that is what they meant, but it was not clear from their very notation itself. If you had removed all the pure plain text from their notations, you would not be you would be quite at a loss to know the difference between f of x and f of x naught, right? And the whole point is, in your language of mathematics, you should be able to make this distinction, this conceptual distinction between a function and its application, right? And keeping in mind, as you said, that the only way often to define a function is by means of its application on some argument, right? So if you look back at if you look back at this notion of at this function application, what Church also said was that function application by this kind of syntactic substitution is actually a reduction of the function, and this sequence of steps actually constitutes a computation, and the computation is purely symbolic, in the sense that you are using only syntactic substitution. Okay. Now, as the point about this emphasis on functions is that just as sets form the basic foundation of mathematics, and therefore you could not use, for example, numbers to define sets, except of course in a meta-syntactic way. You know, you might define a list of sets S1, S2, Sn, but that S1, S2, Sn is not numbers. I mean, they are not numbers as a value domain of interest. They are just symbols for you to play around with, to distinguish between one S and another and a different S, right? So the point was that similarly, since functions are basic to most of mathematics and to any other fields of endeavor, the whole point was to concentrate on the notion of function and clean up the notation in such a way that your new notation is independent of everything else and can be applied in all areas. So, if you are looking at a general notion of computation and you have defined the notion of a function quite precisely and independent of all other concepts where functions are used, then what you could do is you could import this new cleaned up version and use it in every discipline where functions are required. Okay. And then you could define notions of computation regardless of your underlying models. You could define notions of computation for particular models derived from this basic notion of function and function application, and this basic notion of a computation as a series of syntactic reductions. Yeah. And so the whole idea was to really make this distinction clear. Okay. If you look at any of the developments of logic and so on and so forth, you do not underline there is a pure logic, okay, in which there is absolutely no mention of an underlying model or a particular discipline or whatever. The entire logic is itself defined in such a way with axioms and symbols and a language such that you could apply it to any other discipline. So, you could think of, for example, you have pure first order logic which just assumes that there is some domain of discourse and that values are drawn from that domain of discourse. Nothing of the properties of that domain of discourse interferes with your logical reasoning. Okay. So, it just assumes the existence of a domain of discourse, it just assumes the existence of a few function symbols of given arity and so on and so forth, and you develop your theory of first order logic completely independent of any particular mathematical discipline. Once you have developed your theory of first order logic, you have certain logical theorems and logical axioms and logical postulates which are true across any mathematical discipline. So, then you can apply this logic to, let us say, the theory of numbers. So, then you get the first order theory of numbers. So, in addition to the logical axioms and postulates, you also have the axioms and postulates of number theory. Let us say Peano's axioms. For example, Peano's axioms do not come as part of logic, but when you apply logic to number theory, you might use Peano's axioms. And in addition to the logical axioms, you will also have Peano's axioms, and then you will try to derive theorems about number theory. So, that logical language and its theory form a sort of underlying foundation, and when you apply it to some other theory, you have extra axioms and postulates of that theory. So, for example, you could just as well give the first order theory of plane geometry if you like. So, then what happens is that you have this logical foundation in terms of first order logic, and then on top of it you have maybe the theory of real numbers, and then on top of it you have the theory of, I do not know, Euclidean geometry, which consists of. So, in your Euclidean geometry, if you look at the proofs carefully, you will find that you are using theorems, postulates, axioms which are sometimes logical in nature. All your proofs by contradiction are all of that kind. You are using theorems, axioms and postulates of real numbers. That means Euclidean geometry assumes already that you have real numbers. I mean, otherwise how do you have Pythagorean theorems and the converse of the Pythagorean theorem and so on. You are using real numbers as a field, that theory, and on top of it you also have the normal axioms which define lines, planes and points, right, and you are using all of these theorems, postulates, axioms in proofs, and they are so neatly stratified that you can use your circularity is guaranteed in geometry. For example, the lack of circularity in your proofs in geometry is guaranteed, provided you only ensure that you are not using a result which you are going to prove later. That is it. A result in geometry which you are going to prove later, but you can use any results from real numbers, any results from logic that you want. right. So, by neatly stratifying your theories, by resting one theory on top of another as a foundation, you can actually have a better control over what might constitute inconsistency in the theory, right. Similarly, you want our definition of computation also to rest, to form a foundation on which all other theories which use functions can rest, and therefore you can define computations on all those theories, right. So, we require some basic notion of function and function application which is independent of any particular application, which is independent of any particular discipline in which we are talking about computations, right. So, and then since we do not have anything else, you really have to look upon this computation as purely symbolic reduction. Yeah. So, so the questions that coming down to more down to earth things, you have, let us say, a function from natural numbers to natural numbers of this form, and this is a classic case of how, I mean, if I did not give a name to this function, if there were not already a name for this function, then I am defining this function by means of its application on a natural number. Yeah. And the question that raises is, now firstly, what sort of an object is f itself? Okay, f is a name for an object which represents a function. Okay. So, what sort of value is f? Because I can think of the space of all functions from natural numbers to natural numbers itself as a set on which I might define more functions. I might define the set of all functions which transform functions from natural numbers to functions from natural numbers to natural numbers again, for example, right. So, that means this function space itself can be regarded as a set of points, and so what are the objects? They can be regarded as a set of values. So, what sort of a value is this function in the set of all functions from natural numbers to natural numbers? Now, can you represent this value f itself as an object in itself? I mean, so that make sufficient distinctions so that it is clear what is an object of n, what is an object of n arrow n, right. And of course, if you have decided that computation functions are basic to computation, then you can't use sets. I mean, what is done once you have defined set theory in mathematics is to define functions as relations of a particular kind which are also sets. But now you are not allowed to do that because you are considering functions themselves to be absolutely basic. They form the foundation of all notions of computation. So, so then essentially the problem boils down to, can a function be defined without giving it a name? And of course, you are not allowed to use sets, right. And an associated problem is that you should get rid of ambiguity somehow. I mean, function definition. I mean, if I give a function an unnamed function definition like this, then it's clearly a function of two arguments n and m, but is it gmn or gnm? You know, is it g applied to mn or nm? And depending on how you look at it, you might actually get different results. I mean, so there are some trivial, I mean, unless you explicitly, I mean, you have to be somehow consistent with normal function notation and so on and so forth. You can change it a bit to avoid ambiguity, but not too much. I mean, the basic notions should remain the same. So you should also be able to get rid of ambiguity. But essentially, once you have cracked the problem of how to define unnamed functions and treat them as objects in themselves, as linguistic objects in themselves, and define function application in a purely symbolic fashion, then you have the notion of a computation. And what Church said is that whatever you can do with just those two notions is all that is computable. whatever is representable linguistically with just these two notions is the concept of an algorithm. Anything that is not representable by this is not an algorithm. And of course, nobody believed him. Yeah. So, the whole point was that what Church said turns out to be consistent with other theories on computation and so on, right. So, the whole point was what he defined was a lambda, what he called a lambda abstraction. Why he used lambda I am not absolutely certain about, but it was fashionable to use Greek symbols those days for all kinds of things. So, we have to differentiate between function definitions, functions as objects having the same status but distinct from and represented unambiguously. So, functions and values should have the same status, right. And secondly, you should be able to define function application in a domain independent fashion and in as symbolic a manner as possible. Okay. So, the whole thing has to be linguistic and the whole thing has to be symbolic, syntactic, I mean, right. So, right. So, what Church actually used as his lambda notation, which I am not going to use, is this. So, what he said was, I do not need to give names to these functions. This, he said, was this string just represents the squaring function on natural numbers, and I do not have to give it a name. Okay. This clearly tells you unambiguously which is the first argument of the function which calculates n square plus m and which is the second argument of the function, and these arguments are taken one at a time, right. So, he resolved all this problem by just using a local declaration. I mean, in modern programming language terms, that is what it means. You have a local declaration and you have a function has a local declaration or a parameter declaration, if you like, you can take it either way, and a body, function body. Yeah. So, whatever is a parameter of the function is abstracted away, is made local through such a declaration. So, what distinguishes n star n from lambda n star n? In n star n, the n is free. In lambda n star n, the n is bound. There exists a binding of n which that lambda n does. So, it is like a local declaration, very much like whatever we have done previously, right, except that since the whole thing is now, and of course, then once you have local declaration, you also have the notion of a scope, right. So, this is the scope of this local declaration, right, and similarly for lambda m, this whole thing is the scope, and for lambda n, this whole thing is the scope, right. So, you have nested scopes. You have cleared the ambiguity in function application by using nested scopes. But what I will do is I will use this notation which is parallel to the set notation. Yeah, this is like a normal set notation. It is like a normal notation for procedures, for example, in Pascal. So, you have procedure heading or function heading, local declarations, begin, end. Yeah. So, you have this reserved word here, you have another reserved word, and you have a clear delineation of the scope. So, this function, for example, would be represented like this. So, it is you first have a local declaration for m, and then you have this function defined inside, and you have these nested scopes, right. And then function application then becomes exactly like this. So, what does it do? You take a function definition, okay, and apply it. An application is denoted by a pair of parentheses around the function and its argument. Yeah. So, now what you do is very simple. So, this application of G34 is really the application. So, this thing in square brackets, the outermost square brackets is the function to which you apply 3, you enclose the whole thing in parenthesis, and then you apply 4 and you enclose the whole thing in parenthesis. And syntactically it is very simple. You have function application if you have a left parenthesis and a left square bracket occurring one after the other, right, occurring immediately in sequence. And when you have this occurring in sequence, all you have to do is match those corresponding brackets, okay. And now what you do is this application clearly says that it is, you have to replace all free occurrences of M in this expression by 3, and that is what you get here. When you replace all free occurrences of M by 3, the application gets rid of these parentheses and these brackets, and you have this. Now, which is, and it is again clear that this is another application, a left parenthesis and a square bracket, and find the matching square bracket and the right parenthesis, and you have the argument there. And this application clearly says that you should replace all free occurrences of N in this scope by 4, and you have this. Then the rules of your discipline here, let us say numbers or addition or whatever, multiplication, somehow give you this step from here, but that is not part of the lambda notation. Okay. So, the lambda notation just gives you these 2 steps of the computation as a form of syntactic reduction. So, this application is actually G with all free occurrences of M replaced by 3 syntactically as pure syntax. I mean, that means a baby should be able to look at these patterns without knowing any mathematics and do it. Rather, a machine which is much worse than a baby has to be able to do it, right. And once you have done this, the next thing is a syntactic replacement of all free occurrences of N by 4. Yeah. So, I will define the syntax of the pure lambda calculus next time and the computation tools.